Hello, everyone. Good morning. I'm Sherjeel, and this is Yaru. And we will also show you something very, very cool. We've implemented something a lot of fun into NOMAD. So I hope we can do it as much as this guys for us. So I'll describe something we've been working on for a while called FAIRmat. It's something to do with perovskite solar cells, like Yaru was working on. And we decided to bring this into NOMAD because we realized that science moves faster than humans can read. So we knew that at some point, this line, which is the manually curated data where humans can actually understand it, will start, kind of slowing down, and papers being published are going up. So you've got this knowledge background. There was a project, a very cool project called the Perovskite Database Project, and that project involved getting a lot of PhD students to go through a lot of papers manually. It's a very, very tedious task. The impact was amazing. We could actually see trends in the field because all of these papers are written for specific engineering tasks, and then you kind of miss the big picture if it's not put together. And it's in text, so it's always difficult to go in and cut through all the specific engineering tasks and get something that you can compare to the other papers as well. So this project had an Excel sheet where there were a bunch of fields decided and everyone had to fill them in, but because it's a manual task, it's always super, super tedious. And I've done it a bunch of times myself for the project, and I don't wish anyone to do this. It's very, very tedious. So we decided we will not let humans do it anymore. Instead, we'll make something to replace them. So this is the kernel autonomous pipeline. It first has this open source, open access actually, literature watch that keeps on polling the internet whenever there's something new out there. It takes a bunch of sources, finds the PDFs, downloads them, anything that's open access, because that's what, well, we're allowed to see and allowed to process, right? So it's always a good idea to have your papers open access so tools like this can actually use them. And then we run these PDFs through our pipeline, and well, we did it mostly with Claude 7.4, but we run it through any LLM and extract structured JSON out of it. So when you have these long text of papers, you can't really put them in NOMAD and expect it to search and compare and plot, right? So that's where this comes in. It takes out all that text and makes it into a structured schema that you can actually view in NOMAD, and we provide a platform where you can compare it to all the other source sets out there, and also the new data that you're working on right now. So if you have NOMAD in your lab, you can actually compare it to what's out there already by just inputting data there. So we know that LLMs don't really produce trustful data, so we had a little bit of a mathematical filter because we know enough about solar cells where we could do certain calculations on the performance metrics to set up some filters that tells us, okay, does this even make sense? Whether this is something completely out there or the LLM just hallucinated. So we run this filter through. And then we publish everything into NOMAD, so it keeps on updating itself, and without any human intervention, whenever you go to the NOMAD dashboard, you will be able to see more and more data. So the Perovskite Database Project had papers in blue here, a lot of papers, but they kind of stopped here, right? So they published their paper, the data set in around 2021, and they worked over the years, and they had a lot of papers, and I think 40,000 cells came out of those. So we attempted to run this pipeline with the backlog of all the papers that since the Perovskite Database Project, so all these years here, and we tried to make a consistent method of how we acquire these papers and how we deliver them to NOMAD. So this is something that we can always replicate, and if we need to fix along the way, we could. But something where when the data comes out, it's not opinionated or something. It's really just what is out there on the internet. So as you can see, we filmed a great deal of it, and we got like around 7,800 devices in the first run that we did, out of 2,582 publications. So overall, you see there's a trend of efficiency going up. So I must say the scientists are doing a great job there. And to explain how this hallucination thing, eliminating the hallucination part works, we didn't want to invent something super costly because it's a lot of devices, a lot of processes that we're already using an LLM. So we went with some basic filters, and this one just tells us that if so we extract 4 values, and then we just multiply them and check whether 3 of the values multiplied together match the 4. So we have like a cross-reference check on what the LLM produces, right? So this little mathematical check already gives us a good verification on the data. We said, okay, let's test the same idea on the perovskite database project that was done by humans. And as you can see, we have way more devices that pass the consistency check than when I ran the same check here. And the perovskite database project actually produced much less. This is why I say it's very tedious, and we tend to get tired. LLMs don't. So even if they're not perfect, at least they're consistent. And here you can see a rough graph, like a plot of all different LLMs I ran, and you can see they quite vary a lot as well. But Claude, for some reason, was very, very consistent. And I like this because now we're exploring way more fields. You have stability in there that wasn't in the perovskite database, for example. And Claude does a good job of overall covering the precision on different paths. So to make this really work in a way where I can actually come up with numbers as well, I decided, okay, we will take human annotators, experts in the field, and we will get them to go through the same process, the same instructions that we're giving them roughly, and also just run it by them. So we have sort of a ground truth to actually measure performance of the models. What we found is that out of all the extractions, 13 human experts achieved full consensus only on 13% of the extractions, so 30% of the PDs. And this was also omitting a few things where there was text, so I also could verify, so these are mostly numerical fields. So that's quite a lot of variance, and that's why projects like these with LLMs, where especially their open source LLMs, provides a way where at least you can consistently get it. Like now there are experts in the field which don't agree on a lot of things, but the LLM just cuts through that and produces one schema. So what could we figure out with this? So of course we're looking at big data here, and we would like to compare how we did or how the field has emerged after the perovskite database project. And you can already see that the composition of the main layer, the solar cell, the solar layer, has actually, like the diversity has increased a lot. Before, people were very, very much in love with MAPBI3. But now, they like FAPBI3 a lot, but also they've explored quite a bit. And this trend you'll see later as well, that FA-based absorbers are just preferred. And these kind of insights, a lot of times researchers have an idea of this, but it's always hard to, like, it feels like a hunch. It's like, okay, I read X amount of papers or I've talked to X amount of researchers, right? But here you can see a bigger picture over everything that's happening in the field. And then here you can also see that not just the absorber layer that's on the left, but also the other layers, a solar cell is stacked like that, so that's a whole transport and electron transport. That doesn't matter, but you can see here that we can guess what kind of trends are emerging, what kinds of compositional changes are coming. People are getting much more exploratory with their data. We also see that there's a general device architecture change, and the ETL material had completely, like this TiO2 was super popular back in the days and it started to share. And here, you can also see that as the number of devices increase, the exploration, so this area here is kind of like how accelerated of diverse materials were being seen, and that acceleration of diversity, let's say, it's kind of slowing down. So people are exploring less and less diverse materials in the absorbable layer, but at the interfaces, they now start engineering more, bulk cross reduction, of just figuring out how to stack them nicely where there's much less power loss instead of dealing with the absorbable material. And just to show how the data is not just, because we looked at the differences, right? But here you can see this is the perovskite database project data as well as the Perla data added. And you can see there's a continuous trend of how close the performance is, or the metric they're actually hunting for, is getting to the theoretical limit. So this is how far away it is from it. And you can see it's every year it's like a negative 25 millivolts. This was also interesting to see to kind of get us like, LLMs are not doing that bad. Of course, we've brought all this data into NOMAD. So now when the pipeline is running, I think we've reached over 8,000 devices now, and you can just explore them through NOMAD. So it's all in easy dashboards. You're free to do all the different NOMAD actions you can run on them. So anything you like, this is all public data. And if you need to reach it, of course, I'll share the links with you. And we not only wanted to have this autonomous pipeline, but we wanted to allow the human in the loop factor that Ahmed was mentioning, where instead of just me getting the spot to look for PDFs and extract it for you, if you know all this, why not let AI assist you in extracting the same information so you can see how it works on your OASIS before you publish? And we've built in the same extraction routine, but instead of scanning the internet, you provide a PDF and you parse it through NOMAD actions. And it will talk to an LLM in the back and create an extraction out of it and bring it back into NOMAD. Oh, sorry. I hope that works. But yeah, so once you upload your PDF here, let's see, still loading. Yeah. You can upload as many PDFs as you like. Let's say you have a draft paper even. You don't want to deal with manually extracting it yourself. You can go here, run this NOMAD action, and it will create an exit. So you're free to choose any model, and if you need any open source models, you're going to also have this little feature where you can run local models as you like. So this is Perla itself doesn't really care about what model you use. It can be completely local, it can be from anywhere in the world. And now just quickly see the results. So you can see how the solar cell looks like here. Come on. It's very slow. Has anyone seen that flip book where it was Steve Jobs asking people to turn on the Wi-Fi? I don't know. I'll just skip it. So you can take my word for it. It extracts and then brings the data into NOMAD, and you can actually browse it right now. So it's completely public and in production, so you can have a look there. Go to the next slide. Yes. And yeah. And then I'll hand it over to Yaru, and she will show another cool way to extract the same data so you don't even have to use forms.
So I will present a project called unstructured audio NOMAD data. So Shabih talked about LM extraction from PDFs, and we could also do from audios. So I will use the same schema, postcard solar cell schema as a demo, and why we do audio input as for extraction is because researchers work in the lab, and sometimes during your synthesis you have to stop and developer has start to write your parameters or the steps or the chemical rate that you complete in the NOMAD. And what is even more inconvenient is when you are working in the glass box and it's not so handy for you to write something down. So here we could use audio as input that we will record your voice live while you are doing the experiment. So what that does is like we have a UI where you can also log in, use your NOMAD credentials, and it talks to Whisper and also LLM. Whisper to transcribe the audio to text and then send to LLM for extraction. And we will upload the schema to NOMAD, and here you can check the extraction and edit it. So the process looks like this. You speak and there will be audio, and you could also upload a pre-recorded audio as well, and then Whisper transcribe it, extract the JSON schema, and there will be some post validation process that we will do it, and here you upload. We will upload to NOMAD. So as I said that you can log in with NOMAD credentials, and all your data will be stored in NOMAD. It wouldn't leave NOMAD ecosystem. Here I will show a live demo who is interested in reading this. Okay, then I will read. Okay. Hello, this is the test. Okay. I'll read now. Okay. So, this is an inverted P-I-perovskite solar cell on IDO with a self-cesium 0.05, Fa 0.95, light triiodide absorber, MEO-2PACZ whole contact, and C60 BCP and silver on top. The band gap is 1.53 electrovolts, and the active area is 0.16 square centimeters. Under AM 1.5G, it reached 23.2% efficiency with an open circuit voltage of 1.15 volts, short circuit current of 24.6 milliamps per square centimeter, and a full factor of 82%. Oh. I mean, this is an inverted P-I-N perovskite solar cell on IDO with a cesium 0.05 Fe 0.95 light triiodide absorber, MEO-2PACZ whole contact, and C60 BCP and silver on top. Slow. Okay. So the rest I will just paste here because it's usually it's working. So here you can edit if the transcription is wrong. For example, here I will correct some of them. I think also here.
Also, this data stays in the browser, so you don't have to worry of it going anywhere until you hit the green button. It all stays in the browser.
Okay, so yeah, so you see the transcription and you edit it, and then you can click extraction. Okay, so now the extraction is done. You can view it on NOMAD here. Here, yeah, so this is the extracted data. One thing I didn't mention is about here you can also log in and log out using your NOMAD credential here. And also you can also upload your audio here. And you could also, yeah, so in the NOMAD, I think,
It's this one.
V2, yeah.
This one.
Which one?
The second tab. I think it was the second tab. We just moved to the different.
I'm looking for the V2.
V2.
Yeah, so this one? Yeah. So you could find this sand here in the APS and here sand. Yeah. So you can say that you can record your stream voice. You could also upload your audio files, and you could also edit the transcript. And in the future, we want to also do some boost process, for example, to convert this reading to this formula. And also, we want to do maybe to merge several audios into one, because maybe you'll talk about something and then you'll talk another time something, and these are actually one experiment. Yeah, and of course, our goal is to expand schema to any schema that it will be automatically recognized, and you don't need to select the schema as well. Yeah, that's it. Thank you.